Okay, now that you've had a chance to work with the machine learning models on your own, we're going to think about broader use cases of machine learning and artificial intelligence in climate change and climate change related problems. So, in this tutorial, we're going to discuss the many ways that AI and machine learning can be applied to problems that are related to climate change. We're going to learn about resources within this domain where you can go if you want to find more information. And we're going to discuss the issues that can occur when you're deploying AI in the real world on real problems. So let's think about how AI and machine learning can be useful when it comes to problems associated with climate change. As it turns out, machine learning is being applied to many, many problems related to climate change already. This is happening in both academia and also in companies. People are doing research, they're building products, and it's really become a popular thing to ask how can all these advances in AI and machine learning help when it comes to climate change. So, there are many different problems that can be helped by taking a machine learning approach to a data set that relates to climate change. So, for example, what if we want to make better models that can predict extreme weather events? So, we just built a model that can help predict average temperatures way in forward in 2050. But what if you want to know, will there be a hurricane in 2 weeks and where will it land and how severe will it be? You can use machine learning to help use data from the past about storms and things like that to make better predictions about how these storms will play out in the future. Agriculture is another big field where machine learning and AI is coming into play. Agriculture contributes to greenhouse gas emissions through various means, but agriculture is also heavily impacted by a changing climate where we can grow things, how fast they grow, if there's droughts or floods. So there's a lot of data around agriculture. There's a lot of interest in building better, more resilient farms, making them more sustainable so that they don't contribute to climate change and they're not as impacted by climate change. And one of the ways that people do this is by using aerial or satellite imagery to track what's being grown in different regions and how it changes over time. Also, disaster response. As there are more extreme weather events under climate change, we need better systems that can automatically respond to disasters. So, for example, having a drone fly over a region and be able to identify what kind of damage is where, that's something that could be automated through machine learning methods. But importantly, we need to realize that machine learning is not a silver bullet. It doesn't solve all our problems. It doesn't even work perfectly all the time. As we saw here, you have to think about issues of out of distribution generalization when you're applying things in the real world. You also need to think about what kind of data is available to train your model on, and is it representative of the applications that the model will be used in. If you're training your model on farms in the US, will it work on farms in China? That kind of thing. And you need to think about compute power. Some of these models, as they get bigger and bigger, they need large computers and large data centers to be able to train and run these models, and not everyone has access to that, and so the solution won't be available to everyone. And when you're trying to apply machine learning to a new problem, you should always work with someone who has domain knowledge, who is an expert in that area. Sometimes machine learning makes it possible to not really need expertise. Like we saw here, we didn't actually have to know how the climate works. You didn't have to know how an Earth system model works in order to train this emulator. You just have to give it the inputs and tell the model to learn the outputs. But you're going to do a lot better if you actually have an expert involved who can understand where the model might be going wrong, what the nature of the data that you're working with is, and what kind of problems are even worth solving. So in this tutorial, you're going to brainstorm. You're going to learn more about a wide variety of applications and talk to each other about what kind of problems you're interested in and what you think of them. And some of the resources you can use, Climate Change AI, this hub is really great for this intersection of climate change problems and machine learning and AI. It has a lot of academic resources, it has tutorials, it has pointers to data sets. So climatechange.ai is definitely the best place to start. For things about disaster response, there's HADR.ai, which is artificial intelligence for humanitarian assistance and disaster response. And then there's also things like the Journal of Environmental Data Science, if you're interested in how data science and machine learning can be applied to environmental issues. There are also some more general resources for data sets. So the Climate Change AI Wiki has data sets, but there's also these other websites that aren't all specifically for climate change related problems, but are just websites that host data in general. And so Driven Data tries to host data sets and host competitions related to machine learning for problems that have kind of a public good angle. Zindi is a data hosting site that's specific to Africa, and Kaggle is a more general site that hosts a lot of data sets and has competitions where you can try to train machine learning models and see who can get the best score on the problem. So, as kind of describing here, machine learning has the potential to help with many climate change problems, but actually taking a real world problem and framing it in terms of machine learning can be difficult. It can be hard to figure out, okay, what data should I use and what kind of problem do we have here? How do you frame it? What model should be used to be able to solve this problem? All of those details can be difficult, especially if you don't have domain knowledge. And then also, it's just not always the right thing to do. Sometimes there are ways to solve problems that might be simpler than using a machine learning model, might be more robust than using a machine learning model. And so it's just important to keep that in mind. There's an old saying that if you have a hammer, everything looks like a nail. So if you have the tools of machine learning, sometimes it can seem like, oh, machine learning would be helpful here, here, and here, but it's not always the case, and you have to think about what value training a machine learning model brings to the problem that you're working on. It's also important to think about evaluation, as we've been thinking about today, right? You want to make sure that your model generalizes, that you're using the right kind of metric to evaluate if it's doing well, and if it's doing well on held out data and maybe out of distribution data. You also need to remember to compare it to baseline models. So we built a machine learning model today, but we can't say if this is working better or worse than a simpler model would because we've only built a single model. And then you want to think about what differences matter in practice, right? So, for example, in predicting the temperature in 2050, well, we know the model isn't going to do it perfectly. Is it okay if it's off by zero point 0.1 degree, or is that difference big enough to mean that the model won't be helpful for us, that we actually need a model that works so well that it's not even making errors of zero point 0.1 degrees, something like that. What type of errors matter more in the model? And so you have to know that in order to decide if your model is good enough to be used for the application that it's supposed to be used in. So when thinking about machine learning on real world problems, you need to consider, will the data be generated in the same way, or will it be more of an out of distribution problem? Do you expect the relationship between the inputs and the outputs to remain the same? If you use training data to learn an input output relationship, but then something in the world changes and now that input output relationship is different, then your model is not going to be able to capture that difference. How will you perform quality control? If you're using this model out in the real world, how will you actually think about if it's performing well enough to keep being used? Who's going to be checking in on it? Who's going to be responsible? How will the model results actually be used? Who will this information be given to? Will they understand the uncertainties that come from these kinds of models? Or will they think that this answer is the correct answer and there's nothing to be worried about? You want to make sure that when you're using a machine learning model, everyone who works with that model understands its limitations. We also have to think about fairness and equity. So when you think about applying machine learning models, you have to think about, again, where is compute power available? Who will have access to running this kind of model? What is the source of the data? Did the people who generate the data or were involved in the data in some way, did they consent to their data being used in this way? Was the model built and deployed transparently? So can everyone who's going to use the model or be impacted by the model, do they know how it was built, what data it was built on, how it's being used, and who will be most impacted by the model's use? Are they involved in understanding the model, understanding how it's impacting them? And does the model perform similarly across groups or locations? Again, if you train your model on data from one country, that doesn't mean that it's necessarily going to perform well on data from another country because that's a different data distribution. And so you don't want to say, oh, my model works really well, I can confidently deploy it all across the world, if in fact it's performing differently in different groups, on different groups, or in different locations. And then who will be held accountable if the model is misperforming, if there is some problem that comes from using the model in the real world, who is in charge of taking control of that? Okay, so now you have a chance to think about these real world problems by looking at some real world data sets and looking at other examples of people using machine learning and AI and climate change problems. So you can use the Climate Change AI website, the wiki that they have there, to explore and talk with your group about these kinds of issues in real world problems.